Well, hello, everybody. I'm Nick Trefethen from Oxford, welcoming you to our invited talk by Daniel Kressner. A little bit of housekeeping first. We won't necessarily monitor the chat line, though you're welcome to use it. In principle, if you have questions, you should submit them with the Q&A. Though I think in practice, maybe the numbers are controllable enough that we'll be able to be pretty loose about questions at the end. So let me say a word about Daniel Kressner. Kressner is one of the leading figures in numerical linear algebra. He's a German who did his PhD at the Technical University of Berlin with Volker Mermann, and I think that was in 2004. I got to know Daniel through eigenvalue problems, where he made remarkable contributions to linear and nonlinear eigenvalue problems. But he's had many interests, and in more recent years has become best known for his work related to low-rank algorithms and tensors. And I just want to mention that he's both a creator of algorithms and a scholar. And in terms of the scholarship, one of his wonderful publications is, I've got the title here, is his 2013 paper called A Literature Survey of Low-Rank Tensor Approximation Techniques. That's really a major paper, a wonderful reference that's joint with Grassedik and Tobler. Okay, well now Daniel Kressner is a full professor at EPFL in Lausanne in Switzerland. He's been there since 2011. Please go ahead, Daniel Kressner.
Okay, thank you, Nick, for the very kind introduction. So I'm sharing my screen. Okay, does it come out well?
Yes, it's beautiful.
Okay, very good. Okay. So it's a great honor to be here at Zoom and present you my work together with my co-authors, Bernd Beggermann, Alice Cordinovis, who is currently a PhD student in my group, Michel Crosset, Stefano Masse, and Marcel Schweitzer. The last two were postdocs in my group. The title of the talk is Fast Algorithms from Low Rank Updates, and that will be specific to matrix functions. And so let me immediately go to the topic. So considering matrix functions, so given a square matrix n, there are several ways of defining a matrix function. One thing most of you are probably familiar with is a matrix polynomial, where you take a polynomial and you replace the scalar variable by a matrix, and which gives you an n times n matrices determined as a linear combination of the powers of A. Or if A is diagonalizable, you can apply the function to the eigenvalues of A, and then you back transform. And in general, if you have an analytic function, which is analytic on a domain containing the eigenvalues of A, then you have this Cauchy integral formula for matrix functions, where I plug in the F here, and here you have the resolvent of A, and then you circle around the eigenvalues of A. So as matrix functions come in different flavors. So all of you know, of course, the inverse, which fits this definition if you insert the reciprocal function. All of you know the matrix exponential, with the exponential function here, useful in implementing numerical integrators for ODEs or PDEs. Matrix sign function plays a big role in control, square roots for Dirichlet Neumann maps, for stochastic processes, for sampling from different distributions. The matrix logarithm, most famously known for the relation that the logarithm of the determinant of A is the trace of the matrix logarithm of A. Rational functions. So things I have worked on more recently in that context, and which has become quite famous, are things like graph convolutional networks, which come back to this idea of signal processing on graphs, where one considers data living on a graph, on the nodes of a graph, and one wants to do some filtering or denoising of the data, taking the topological structure of the data into account, that it lives on a graph with edges and nodes. And instead of the standard Fourier transform, one uses the eigenvectors of the graph Laplacian to transform the signal. Then there's filtering, and then it transforms back. And it has been recognized quite late in this field, I would say, that is actually a matrix function. So you apply a matrix function f to the graph Laplacian associated with this graph, and get f of L, that's your filter, and it's applied to the signal x and returns a y, which could be, for example, the denoised signal. Now that has been taken over and has been extended to graph convolution networks, where are huge graphs now in applications where things like this are used. What's interesting in the context of this talks is that if you remove an edge, or if you remove a node, you add a node or you add an edge, that corresponds to low rank changes in the graph Laplacian. It will come later on. Another object we are going to need is the Fréchet derivative, which if you add a small perturbation to the matrix A, and then you do the Taylor expansion, that gives you the first term in the Taylor expansion. It's a linear operator, the Fréchet derivative applied to the perturbation E. And that comes into play, for example, if you define some target function, if you, for example, think that your data evolves according to a heat diffusion on a graph, or if you have a parabolic PDE governing your data, and then you would like to optimize something. For example, you would like to optimize the graph, you would like to learn the graph, then you have to solve an optimization problem. And in the moment you use a first order, like a gradient method, you have to differentiate, and then somewhere you have this matrix function, like the matrix exponential describing your diffusion, which by the chain rule you also have to differentiate the matrix function. So that would be an application where you need to evaluate the Fréchet derivative. It's a quite heavy object for a large n. If you have a 100,000, if you have a graph with 100,000 nodes, this is a linear operator on matrices of size 100,000 by 100,000. So that's something which is not easy to compute at all for general matrices E. And what got me into this is this one question about, so that's the start of the talk, is there something like a Sherman Morrison formula for matrix functions? So the Sherman Morrison formula is probably familiar to all of you. So if you have a matrix A, which is assumed to be invertible, and you change A by a rank 1 change, so BZ transpose, B and Z are vectors. So what happens to the inverse? And so you get A inverse again, and then you have a correction, and this correction term can be computed by solving linear systems with B and C. And what's important in our context is not the precise form, which you find on Wikipedia, for example, but it's actually the fact that this change has again the rank 1, because you have an outer product of vectors again here. So the inverse of a rank 1 change of a matrix is the inverse corrected by a rank 1 change. So there's some kind of invariance of rank 1 corrections under inversion. And I highly recommend you, if you're interested in this and applications of Sherman Morrison, derivations, history, there's a very nice series of blog posts by Nick Hyam, more than 50 now, on different topics primarily related to matrix analysis, numerical linear algebra, and even recommended by persons working on machine learning. Stop reading Medium posts on machine learning and start reading Nick Hyam's blog posts instead. I highly recommend that to everyone, not only those in machine learning. So that's really a great resource of getting update on the current state of the art in matrix analysis and numerical linear algebra. Now, what would be really cool would be to have a Sherman Morrison formula for matrix functions. Why is that? It's because the Sherman Morrison formula for the inverse is at the bottom of many techniques in scientific computing, things like domain decomposition, then other model reduction techniques are implicitly based on this theorem that the rank 1 change of the inverse is the inverse plus a rank 1 change. If you have a similar formula for the matrix exponential, that would have important implications for time integration, for example, that you can derive parallel algorithms, network analysis, signal processing of graphs would become much easier, and so on. So if that's my conjecture, the first thing I would do is I would go to Matlab and try it. But before that, maybe I look into the reference, a standard reference of the field by Nick Hyam, functions of matrices, which states that formula is indeed true if A is the identity matrix. So if I have the identity matrix, change it by rank 1, I get again the identity matrix. So I need to assume something on F, that the F of the identity matrix again. Let's say. And then I get a rank 1 change with something which looks a bit like a finite difference quotient here. And a similar formula has first come up in the context of symplectic integrators by Celluloni and Isales. And a general case, I think, has first been indeed appeared in a book by Nick Hayem. So now let's see whether this also holds for general A. So I would type it into Matlab. Just a random matrix A, I take the minus here so that the exponential keeps controlled, doesn't get too large, and I choose just random vectors B and C. And then I look at the rank of the difference of these two matrices. So if I had something like Sherman Morrison for matrix function, the result should be 1. It's a 200 by 200 matrix, the result should be 1. The result is 11. So maybe there's a Sherman Morrison formula with a rank 11 correction for the matrix exponential. But if I try it again, I suddenly get 16 different random matrices, different random vectors. Once I get 11, once I get 16. So what is going on? This is easily explained once one knows a bit more what the rank function of Matlab is actually doing, and if one looks at the singular values at the difference. So one looks at the singular values of the difference of this matrix. So this is what for which we computed the rank and for which we hoped it has rank 1. Doesn't have rank 1. Instead, the singular values, so we have the singular values ordered from the largest to the smallest. This is a logarithmic plot, so we start with a singular value of around 10. And then we drop very quickly, only 10 singular values, about 10, 11 singular values are larger than 10 to the minus 12. And the rest here, this is just round of error. So in exact arithmetic, this would go further down very, very quickly. So what Matlab is doing is it computes the singular values and then counts the number of singular values which are larger than 10 to the minus 16 times the norm of the matrix. And that's the numerical rank. And it's doing this because it's simply an ill-posed problem to compute the rank of a matrix in double precision arithmetic. So it does the next best thing and tries to find nearest rank R matrix. If that error is below round of error times the norm of the matrix, it declares this matrix to have rank R. And what's behind here is the well-known Schmidt-Mirsky-Eggert-Young theorem that the nearest rank R matrix of a given matrix A achieves an approximation error which is governed by the singular value R plus 1. So if that singular value R plus 1 is small, I find a very nearby rank R matrix. And what it means in practice, if you have a quick singular value decay like this, that's a good sign because it means that this matrix A, or in this case, it's the difference matrix here, can be replaced by a low rank approximation. But that's something which is a posteriori, so it's quite meaningless. It's you do all the computations and then I compute the singular values and I tell you, well, you computed this full matrix, but this matrix actually has a very steep singular value decay. So maybe you shouldn't have computed this full matrix in the beginning because there's a much better data sparse format for that matrix, but it doesn't help you very much because you already invested into computing the whole matrix. So in this talk, we will discuss how to compute a low rank approximation of the difference without computing the matrix first. So 200 by 200 is of course still feasible, but think about 100,000 by 100,000 matrices and will quickly become infeasible to compute this difference, let alone storing the difference. So in this talk, we talk about the construction analysis, also the application, what's in the title, getting fast algorithms from that low rank updates from fast algorithms for approximating the difference here. Okay, so let's start with the Taylor expansion. It's always a good start to get a bit of intuition what's going on here. So this is the matrix exponential. You plug in the matrix A in the standard Taylor series expansion for the exponential from your calculus class. That also converges for all matrices A. And if I truncate, for example, after the third term, after that term here, the Taylor series expansion and look at the difference between these two matrices. So I have, that's the truncated Taylor expansion for A plus BC transpose, the exponential. And then I subtract the Taylor expansion for the exponential of A. And what you see here is that you get b, you get, when you take the square, you get something with a times b and some mixed terms, you get a cube, a square b, and so on. And on the right-hand side, you get something like A transpose times C transpose, and so on. So it's probably not hard to believe me that what can be, what appears here are outer products of vectors of the form AJB times C AI transpose C. So there's some powers of A multiplied with B on the left factor and some powers of A transpose multiplied with C. So note that these constant terms here, they cancel out, and what remains are only terms with a vector B inside. So the difference after this truncation, the difference is contained in linear combinations of outer products of elements from these two spaces here, from these two subspaces. So the Taylor expansion gives you a precise element from that linear combination, but in general, what we want to view it, we want to view it as being contained in outer products of the subspaces. And let's make this a bit more abstract. So I define two subspaces, and one is you take the vector Z, and then you multiply it repeatedly with A. That's called a Krylov subspace. It's behind all modern techniques for solving large-scale linear systems or eigenvalue problems, behind the Lanczos method, CG, GMS, and so on. But the difference here is that I take a second subspace, and with another starting vector D and the matrix B, and then I consider all tensor products of elements from these two subspaces. Or in terms of matrices, I consider all linear combinations of outer products of vectors from these two subspaces. So if these subspaces both have dimension k, all linear combinations have rank at most k in here. This links back to this observation that we are looking for low rank approximations. And this kind of subspaces were not new. This kind of tensorized subspaces will play a prominent role in Krylov subspace methods for Lyapunov equations, tensor equations, functions of matrices with Kronecker structure, and also in divide and conquer methods for matrix equations. And we would like to use them for updating matrix functions, because we have already seen in this context that via the Taylor expansion, we see them coming up here. And there are two other useful characterizations for the analysis. So one is that you can view as the starting vector CD if you take the outer product, and then you multiply it with bivariate polynomials in calligraphic A and B. So I did a lifting of the two matrices A and B into n squared times n squared matrices. Note that calligraphic A and B with this Kronecker product here, they commute. So I have a huge n squared times n squared matrix which commute. I evaluate this polynomial in these two matrices, multiplied with this rank 1 vector here, and all these polynomials give me this space. So that's a very important connection. It's behind, in the standard Krylov subspace methods, it's behind all the convergence analysis which exists. This polynomial connection links you to convergence analysis of GMS, CG, etc. in the standard Krylov subspace case to polynomial approximation problems. Another way of viewing this is if you have two bases of these two subspaces, you have this matrix product with a small k times L matrix in between. So we have already seen that from the Taylor expansion, it's probably a good idea to search for approximations in that space, but I would not like to be stuck with the Taylor expansion because, for example, for the exponential, it's probably if the matrix A is real, a Chebyshev expansion would converge more quickly. So I would not like to be stuck to a specific polynomial approximation, but I would like the method to choose this approximation, the quasi-best approximation at least. And from linear systems, one can try some things, trying to determine these coefficients here, which combine these outer products of vectors from UM and VM. And if you try some obvious things, this actually do not work. They do not have polynomial exactness in the sense that these formulas become exact for low degree polynomials F, which is something that you really would like to have if you use the Taylor expansion and truncate after the third term, and that's going to be exact for third order polynomials. You would, whatever method you develop, you would like to have the same property. It would be a bit stupid to not have this polynomial exactness property, and would be very difficult to derive, say, anything useful about the convergence of these methods. And there's a nice observation here, which is often used in matrix functions. So often you can compute quantities associated with matrix functions by embedding them into larger matrices. And then you compute the matrix function of this large matrix, and then you extract from blocks quantities, the desired quantities. For example, if I would have A and A here and some matrix E, then I would get in the 1-2 block of F calligraphic A differential derivative of F at A in the direction E. If I plug in A plus BC transpose, you're getting the difference between F of A plus BC transpose and F of A in that block. And there are many such formulas. You can compute higher order derivatives via clock generalizations of so-called Opitz matrices, some finite generalizations of finite differences to matrices. So this is really a useful tool to think about embeddings into larger matrices, applying the matrix function, and then you can extract quantities. And it works very well because we have this general purpose, very solid, very good implementations of matrix functions, for example, in Matlab for the matrix exponential, matrix square for all standard matrix functions that come up in application. They can really facilitate that functionality to compute our quantities. And here, that's of course not something we would like to do, but it's a theoretical construction. We of course would not like to compute the matrix function of a 2n by 2n matrix. If we just want to get this update here, remember that we would like to do this for very large matrices, but it tells us what we have to do in order to get this coefficients there, because we are going to compress the matrix. I will skip this derivations here, so this is just for completeness. So essentially what I have to do is I have to compute that connection gives me a recipe that I have to compute a function of a small matrix. So M is the dimension of the subspace, which will be small. Think about dimension 10. So it will be a 20 by 20 matrix. I evaluate the matrix function. I get a 10 by 10 matrix, giving me the coefficients, this linear combinations of outer products of the vectors from UM and VM. And that gives me the approximation. That gives me the coefficients of the approximation. And this gives polynomial exactness. So it's polynomial exact if you use Krylov subspace up to dimension M, requiring M matrix vector multiplications, then I'm going to recover the exact difference here. And that's already it. So I use the standard methods for computing basis of this Krylov subspace. This is called the Arnoldi method. It's a refinement of Kram-Schmidt. I compute a small matrix function, I get this approximation here. Works very well. So if I use, for example, this is just a plot here to show you the convergence. If I have the exponential of a symmetric 100 by 100 matrix with a relatively wide spectrum, and then I do a random rank 1 change, and then the method converges after around 45 iterations. And let's apply this to some applications. So one application of matrix exponential is communicability measures of graphs, where you take the adjacency matrix of a graph and compute the matrix exponential. Look at the diagonal. The diagonal tells you something about the subgraph centrality. And the nodes with the largest entries are somehow the most important nodes. And then you normalize with the trace so that everything sums up to 1. That's rather difficult to compute. So computing the diagonal of a matrix exponential is not easy it's not an easy quantity to compute. There's no easy way. The state of the art is to compute one diagonal element after the other by using a connection of the Lanczos method to quadrature. It's fairly expensive, so you need to run this n times to get all n diagonal entries. And once you have done this very expensive computation, you would not like to redo this computation if you just remove or add an edge. And that's actually an interesting element to study. So that tells you something about the importance of the edge. If you remove it and its centrality changes a lot of these nodes, then it's probably an important edge. And removing or adding an edge corresponds to a symmetric rank 2 change of the adjacency matrix. And so we can apply our method. And if we apply our method, we go to a relative high accuracy, 10 to the minus 6. And we do, for example, for 36,000 by 36,000 matrix, so a graph with 36,000 nodes. then running 10 updates requires you around 2 seconds, whereas a single computation of the diagonal entries would require 150 seconds. So doing this 10 updates by recomputing diagonal entries 10 times from scratch would require you 1,500 seconds. And so this method reduces it to 2 seconds, and that has not been known before our work, that you can actually execute these updates of matrix functions so efficiently. Let's go to the convergence analysis, because there are some interesting elements. I would like to sketch this a bit. So we would like to get a priori bounds on this approximation error, which we obtain by our approximation. And so why would we like to do this? We would like to understand which functions can be are well accessible. Can we also, also later on, maybe you would like to use other methods instead of polynomial Krylov subspaces. You would like to use shifted inverses of A, which give you rational Krylov subspaces. So it's interesting to study when can you expect that this method works well a priori, but also for choosing the parameters in the method. And the strategy is quite standard for getting approximations to Krylov subspaces applied to functions, but there are a few hiccups here. So first of all, we have this polynomial exactness, and that because these two formulas, these two sides of the formulas, they are not linear in A or B or C, but they are linear in F. They are linear in the function F. So you can actually, if this formula is exact for polynomials, you can actually replace F by both sides by F minus P for any polynomial P of degree at most M, where M was the degree of the Krylov subspaces. And then we just have the bound norm. And there's just, I would like to understand in quotation marks, because that's actually the difficult part. So I would like to somehow have bounds of the form. For that purpose, we need somehow for F replaced by F minus P, we need to be able to replace, to bound such quantities, the norm of the difference of matrix functions. So that is really a question about the Lipschitz constants for matrix functions. And by using line integrals or other tricks, you can actually reduce this to the question of trying to bound the norm of the Fréchet derivative of a matrix function. And if you know a bit the field, that sounds like José Palencia for the Fréchet derivative. So let me recall the seminal result by José and Palencia, which just won the SIME activity group on linear algebra best paper prize. And it states the following. So I have this matrix function F of A. F is analytic on some domain omega. But now the domain omega should not only contain the eigenvalues of A, but should contain the numerical range of A. So which is the set X transpose AX, which includes the eigenvalues of A, but is potentially much larger. And so I have to pay a bit by bounding F on a larger domain instead of the eigenvalues, but in return, I don't need to diagonalize A or commit any other crimes in order to get a hand on the norm. So the result tells me that I get the maximum of F on that domain, and with this constant 1 plus square root of 2. If the matrix is symmetric, this holds with constant 1, or if it's more general, if it's normal. And for non-symmetric matrices, it needs to be at least 2. And José's conjectures actually states that this bound holds with 2, which is slightly smaller than 1 plus square root of 2. So this conjecture is still open, not clear whether it holds. There's a lot of numeric evidence that this is true. But 1 plus square root of 2 is, I think, good enough for most purposes. And so this question now, where we get something for the Fréchet derivative, this has been studied a lot in operator theory in the context of double operator integrals. And there's a very nice overview article in the AMS notices by Anna Skripka, summarizing the field. Most of this field focuses on normal matrices or normal self-adjoint operators. But here we are in a situation where we are interested what happens for non-symmetric matrices A. So even though there are a lot of connections between what I'm going to say and this whole field of double operator integrals, the questions are slightly different. So here the focus is really on different norm settings and infinite dimensional, so operators on infinite dimensional vector space, where I'm more interested in let's say, the 2 norm and finite dimensional vector spaces. And but the objects are quite similar. So these double integrals come in via this connection to what I like to call bivariate matrix functions. The definition is not so important here. What is probably to connect this, if you plug in a polynomial, you're getting back the matrix representation of this operator corresponds to the bivariate matrix polynomials I've shown you before. That's maybe the first interesting aspect of this definition here. And the second interesting aspect is if you, this is defined for bivariate function f, if you plug in the finite differences here, so the standard finite difference is what you use in calculus to define the derivative. So if you use that here for scalars x and y, and for x equals y, you take the derivative of f, of a scalar function f, and here you take the finite differences of x and y are different, and you plug in that function into the definition. What you get here on the left-hand side is the Frege derivative at a, if you use b equal to a transpose, in the direction c. So in order to be able to get to Frege derivatives, I actually find it useful to go to a much more general definition of bivariate matrix functions, and then we can go back to Frege derivatives. So for that definition, Michel Crozet and I show that one can extend this result by Crozet and Palencia. And the result states something very similar. So f now, our scalar function, I need to bound this on the numerical ranges of a and b. And then I get an upper bound on the operator norm of this big linear operator. And I get a constant here, 1 plus squared of 2 squared. So I have a squared instead of the constant before. And you can imagine that for d variate function, we actually have a power d here. This exponential growth of the constant cannot be avoided, but it could be 2 to the d. So it's easy to find examples where this constant grows 2 to the d. And what we can prove is 1 plus square root of 2 to the d. The proof is relatively simple, essentially mimics a bit the proof of Crozet and Palencia to get a matrix valued version, and then one applies it 2 times to this operator integrals. And now, as a corollary, we get a number of interesting things, which I believe have all not been known for matrix functions. So the Frege derivative is bounded. So the operator norm of the Frege derivative is bounded by the maximum of the derivative on the numerical range of a times that constant. We also get a Lipschitz constant, where we get something which you would expect, something like the supremum of f prime times this constant. But now you need to take the supremum on something which contains the numerical ranges of a plus d and a. And then in turn, we also get our desired error bounds, so which links the convergence of our method to polynomial best approximation. So we get some constants, and here you get the polynomial best approximation minimized over all polynomials of degree at most m minus 1. The error of f prime on the numerical range of a and a plus bc transpose, the best approximation error by this polynomial. And if you know a bit polynomial approximation, this tells you, for example, if f is analytic and a plus bc transpose are symmetric, you're expecting exponential convergence. You're expecting very fast convergence for this. So especially if your function is even entire for like the exponential, you're expecting super exponential convergence. So that a priori result really explains the fast convergence of our method we have observed before. It also tells you if you have a nearby singularity. So if you, for example, have the inverse matrix square root and A is very ill conditioned, then the singularity of the inverse square root, which is 0, of course, is very close relative to the width of the spectrum of A. And then you can also expect that this polynomial approximation will not be so great. And then one can actually extend this result to rational Euler subspaces, which involve shifted inverses of A, and arrive at the rational approximation problem. And that result allows you to tune the denominator of your rational approximation, which in turn tunes the shifted inverses, which you use in the construction of the method, to get a much better approximation here. So that result in it's really useful to understand the limits of polynomial approximation and also to design a method which is based on rational approximation. Now, having this method and having understood the method to a certain extent, one can now go ahead and try to use this low rank updates in a way that Sherman Morrison has been used a lot in scientific computing for matrix inverses and solving linear system. And the idea is relatively simple. So the dividing conquer method for matrix functions. So you decompose A into a block diagonal matrix plus low rank. So you hope that this is possible. For example, if A is banded, it's certainly possible. I will discuss a few more examples in a minute. Then you compute recursively, dividing and so on, the matrix functions for the diagonal blocks. And in the conquer phase, you use the low rank updates to compute the difference between the matrix function of that object and the matrix function f of A, which the difference between A and A tilde is exactly this low rank change. And our method are especially suited for this. So that's why we derived our method exactly for this task. So that's the conquer phase. Use our low rank update algorithms to approximate that difference. So, and the complexity, if you make some idealistic assumptions, so bounded rank, so in reality, maybe the ranks of this off diagonal blocks for some applications may grow logarithmically with n, so they have to pay some extra factors here. Also, the convergence is usually not independent of n, but if you use a good rational approximation, for example, you may also only pay some extra logarithmic factors here. But in the idealistic assumption, bounded rank and convergence independent of n and fixed accuracy, we get O of n log n complexity for general matrices. And for banded matrices, where something special happening, discrete of subspaces and this approximation here are sparse again. And if you exploit this sparsity, you actually arrive at a much simpler method, which I cannot discuss here. I refer to our technical report for that purpose. And you arrive at an O of n method. And so that's really cool because in general, for such matrices, the general purpose methods are all O of n cube at least, like the matrix exponential. So you can potentially, if these assumptions are true, you can reduce from n cube to n or n log n or n times some power of log n. And the output is on every level in the on every level of this recursion in the conquer phase, you get some low rank update. So in the upper level, you get a low rank update here. Then you get low rank updates for f of A11 and f of A22, and so on. And then you get low rank updates here. Plus at the very end, at the lowest level of the recursion, maybe if the matrices are of size 500 by 500, you explicitly compute the diagonal blocks, and that gives you the final piece on the lowest level of the recursion. And if you look at this, I'm a bit familiar with hierarchical low rank structure. This looks very much like hierarchical off-diagonal low rank matrix or hierarchical semi-separable matrix, which is used a lot for solving for fast solvers for integral and differential equations. So we get a structure which is not new, which is quite familiar and can also be then we can post-process this using existing tools here. The scope of this method is, as I already mentioned, banded matrices or sparse, more generally sparse matrices with reasonably small edge separators. So you can use like tools like Metis or other clustering tools to find small edge separators, so that, for example, 2D PDE discretization still have relatively small edge separators. Graph Laplacians for graphs with community structure also have small edge separators. Small edge separators or low rank edge separators translate into a low rank update here. And that's where this divide and conquer phase really makes sense. Discretized integral equations, also other matrices like triplets, Hankel, block triplets, block Hankel matrices, satisfy these assumptions here that you can decompose this matrix in this form after a Fourier transform of that matrix. And that's behind a lot of new methods now, super fast methods for solving linear systems with triplets or Hankel structure. And we are not the first to come up with fast methods for matrix functions of featuring hierarchical low rank structures. So But we are the first to come up with the divide and conquer method, and the main competitor in these existing methods are matrix iterations, which are used in existing iterations, something like scaling and squaring or design function iteration, and implement this in data sparse arithmetic. And then, but where the disadvantage is that you often have to multiply or you have to invert with matrices in this hierarchical low rank format, which is relatively heavy, computationally heavy. It still has similar complexity and polylogarithmic linear complexity, but in practice we are quite a bit slower. Here's an example to give you, a detailed example to give you some insight here. So I will not go into details here. You have a fractional diffusion equation, and it's a standard derivative in time, but fractional derivative in space here. And if you discretize this with Greenwald, Letnikov, find the differences, and then you use the exponential to resolve in time, you are going to get the exponential of a dense matrix, but these dense matrix features hierarchical low rank structure. And now if you increase the decrease of freedom, so in space, you get larger matrices. The divide and conquer method grows quite slowly. So for example, for 8,000, it uses 3 seconds. The competitor, which is the scaling and squaring in HSS arithmetic, needs 3 times more time, and the dense solver is still capable of solving that, but it's quite on the edge. It's 70 seconds, but here really the problem becomes memory issues that you cannot store such a large n times n matrices, so that fails also for 32,000 by 32,000. Divide and conquer is still faster because it really goes directly after this low rank structure, while this goes more indirectly via this hierarchical low rank arithmetic. And so just a few more examples here. Sampling from a Gaussian Markov random field requires you to compute the matrix square root depending on the resolution of the random field. You could get a matrix like this. Divide and conquer computes the entire matrix square root in 13 seconds. The inverse matrix square root pops up, for example, in the Neumann to Dirichlet map, the inverse of the Dirichlet to Neumann map, which you, for example, need to use in, for example, in absorbing boundary conditions for wave problems. And if you take a relatively fine discretization, divide and conquer is still capable of computing the whole map in 37 seconds. And I'm not aware. So the competitor would require at least, I think, 120 seconds for this problem. For subgraph centrality, so we use the network, and then we use the Metis to compute separators. And so we can compute the whole exponential, in fact, only the diagonal of the exponential, in 193 seconds. And the closest competitor would be this quadrature-based method I mentioned before. I think for that example, it requires at least 3,000 seconds. That brings me to the conclusion. So low rank updates of f of a are cheap. They're as cheap as Credo subspace methods for computing f of a times b. And that really comes out in this a priori convergence results. So the kind of what you have on the right-hand side is very, very similar to the convergence results for f of a times b, which are well understood. So they're quite cheap. You can really address very large matrix functions here. There's an elegant convergence analysis via an extension of the Crozet-Palencia result and using bivariate matrix function and specializing it again to Fréchet derivatives. And I've hopefully convinced you that this can be a useful basis of divide and conquer methods. You can find more details in this references here. Thank you for your attention.
Daniel, thank you very much. That was